Hello, everyone. In this video, we're going to talk about another population growth model. So we haven't talked too much about populations. We've been really looking more at just sequences and how they work. Now we're going to really kind of use a model that's very often applied to populations. So here we have a sequence, P1, P2, P3, and on and on. And what is Pn? This is going to be the population of some uh, species or whatnot at time n. And uh, the idea of a logistic growth model is that populations don't have sort of a stable growth rate. So the idea is if you have some kind of island, say, and you have, uh, some species living on the island, then maybe at one time, you have a few um, organisms, and then at a certain point, they grow, and then at another point, another generation, they grow again. But because there's sort of a limited amount of resources on that island, there's kind of a pushback that says, okay, well, if you get too full or too crowded, that growth rate is going to go down and down and actually start turning into kind of a contraction, is the idea. So you have a growth rate. The idea of a logistic growth model is to say that yes, things will grow if there's enough elbow room, is what they call it. So, and in particular, there should be some kind of capacity, some notion of a letter C, which we'll call the capacity for the existence of sort of the population. And you should think of this as sort of an upper bound on what you can get. And then when we have this notion of capacity, we can talk about elbow room in a more uh, mathematical way by saying, okay, well, the capacity is sort of your maximum population. And so if you subtract off your population from the capacity, that's how much sort of room you have to grow, that elbow room that you would have to grow in a population. Great. So now these numbers can kind of vary widely um, because your population could be, you could have a huge island or a planet or whatever. Um, or you could have a very small petri dish or something. And so one thing we often do is we're going to um, kind of normalize, if you will, well, or sort of make everything relative to something between 0 and 1. And the way we do that is we sort of think of percentages. So we say, all right, well, uh, let's forget about just the values of Pn and C, but let's talk about Pn and C, and we'll divide Pn by C, and this is going to be what's known as the p-value at n, and we put a lowercase p there. This is the p-value. And what does it mean? So it is, which is the percentage of capacity of which of your capacity. Sorry, the population percentage is what I want to say. Okay. Let me say it this way. So which is the percentage. So it's the percentage, which is the percentage of your capacity, of the capacity that is populated. Okay. So, okay, so this is the idea of the p-value. And so let's summarize, and then we're going to add the growth rate in order to get the logistic growth equation. Now, we'll look at a few examples of how this all works out in the next video. But right now, our goal is to sort of get the recursive formula for a logistic growth model and to understand what it is that we're actually getting in our sequence. So let's put this down as what we're interested in. So the logistic growth model has the following features. So the sequence is actually not the sequence of populations that we were interested in above, but sort of the sequence of the p-values. P-value sequence. And of course, you can get the populations by multiplying these p-values by the capacity. The next thing that we want to consider is how is the growth rate affected by our p-value? So the growth rate um, at time n is a fixed rate r times your sort of elbow room, which you can think of as 1 minus p sub n. Okay, so where r is a fixed rate. And let's think about that for a moment, see if we can understand it. So r is some fixed number, maybe like 3 or 2 or something like that. It's saying, okay, in a situation where there's no p-value, in other words, where you have a very small population, a lot of room to run, you have an idealized rate. However, if your p-value is close to 1, that means that the percentage of the capacity that is populated is almost 100%. So if this is very close to 1, then this is very close to 0, which means your growth rate is very close to 0, meaning you're shrinking. There's too many people. You're almost at capacity, or too many of your species, and your population starts to shrink. So this factor is a sort of the elbow room factor, and it will contribute to your rate, your growth rate. So this is like your elbow room percentage is the way to interpret that. And then this all leads to the recursive equation, a recursive formula for a logistic growth model, which is, well, we have the population, or your p-value at time n, is just your p-value at time n minus 1 times your growth rate. In other words, that's your growth rate is telling you how much to grow in one step. So you have to multiply, sorry, let me call this n plus 1. We'll go to n. We have to multiply by our growth rate of time at time n. So I adjusted this so that I'm moving up 1 from down below, but you could easily have put n minus 1 here. So again, what is the idea? If I know my population Pn at time n, then my growth rate for that next step is this r times 1 minus Pn. And so I'm going to multiply Pn by the growth rate to get the next p-value. Okay, so this is the logistic growth model recursion, recursion, recursive formula. In the next video, we'll look at a few different examples of this and see how these models work up to some interesting behavior. All right.